In this topic, we will be dealing with in IIoT analytics. And before we go deeply in the details, we will have a quick overview. We will explore with the analytics, and we will talk about what is the significance and in terms of the Internet of Things, and then we will look how the analytics are built and examine the different stages and complexity levels from basic monitoring up to the advanced prediction and decision making. And we will also see a real world example on the condition monitoring of a rotating machine in a power generation plant to see how the analytics actually work in practice. And in the second topic, we will go through the virtual representation of physical assets, which is called digital twin, and we will explore how we can use the digital twin for machine performance, health monitoring, and how we can do online anomaly detection using the edge analytics. So this topic is a combination of overall what we are going to see is a combination of concepts, technologies, and some practical examples. And all aim to show you how, and the main aim is to show how analytics transforms industrial operations. This is very crucial value addition. And basically this whatever we are doing is the value addition. Okay, right. Okay, so right. Okay, so now let's begin by understanding two key terms, analysis and analytics. Okay, and how they are related to each other in the context of IIoT. So with the continuous advancements in the technology, uh, computational resources and the data storage have become highly accessible and affordable, and cloud computing has played a major role here, uh, enabling the rise of the big data, which means we now have more data available than ever before. So, what's even more powerful now is the combination of this technology with the free and low cost tool sets. So, like analytics and statistical analysis and analysis tools and network data access, even the forecasting platforms. So these have allowed us to apply the traditional analysis techniques at much larger scale than was previously possible. So what exactly the analysis is? In simple terms, it is the process of breaking a complex problem into small manageable parts to help us make sense of what is happening. And analysis is often done on the historical data, so it helps us to understand the past. This is an important thing. Okay, so here we understand the past of the process or the phenomena. Um, on the other hand, the analytics on the other hand takes this one step further, and it builds on the results of the analysis. So the analysis is providing us is feeding So the results of analysis actually fuel the analytics, uh, and it builds on the results for the analysis to develop the tools and models that can predict the future. And this helps us to understand, and analytics help us to build future or future behavior, uh, prediction about the future behavior. Okay, so this is where the techniques like forecasting and the machine learning, they actually come and play their role. So in fact, today even the software vendors have combined both analysis and prediction into a single term. And once when we start learning the things, we actually combine them, but that is not good. So we have to keep this part separate and the analytics part separate. So these are two separate parts, and this will help us to understand and bring the proper solutions. So it is important to understand the past before we go for the future. Okay, so these are two different things. Now let's look at the analytics, why it is important, especially in the context of the IoT. So with the emergence of IoT devices, we are having enormous amount of data. And for example, a jet engine can produce around 1 terabytes of data in like 5 hours. So now imagine hundreds of such devices running across a plant or a fleet. It becomes clear that without efficient tools to analyze the data, it's nearly impossible to extract the information. So one real world example comes from the General Electric. They have been monitoring their aircraft for about 15, the aircraft's engine and power systems for about 15 years. And their analysis shows that even if they are able to make a 1% improvement in the efficiency, that will enable them to get 270 billion dollars profit, and this is a big thing. So that's the power of data driven insights. Okay, so the data driven insight is very important, and this is where the big data technologies are stepping, and these platforms are designed to scale up the analysis by handling the massive data sets. And the goal of the big data analytics is not just to process information, but also to discover the hidden patterns and identify the value, and support the decision making. So it's all about um, anything is happening. So we have a lot of data, and from the data we do some analysis, and then we do analytics. Okay, and these all things are actually helping the decision makers. Decision making is the correct, and these days more and more we use the AI for good purpose, the better decision we will come up. So in summary, without data, or you can say that um, data without analytics is just a noise. So but with the we should write without data without analysis is just a noise, is equals to noise. Okay, so to use use right tools and strategy um, will add will bring new or added value to our assets and to industrial setups. This is very crucial. Okay, so now that we understand why analytics is important, let's explore how actually to build the analytical system. So there are, for example, the one way is mainly there are two main approaches. One approach is about one approach we call it rule-based approach, and in this approach we have such kind of thing like if and then rules, and this approach is based on the predefined logic to make decisions or extract insights from the data. So these rules are basically the domain knowledge based, and expert input or established best practice. Domain knowledge, or you can say that established best practice. Okay, or someone expert's opinion. Rule-based systems are usually deterministic and easy to interpret. They are good, easy to interpret, and this makes them useful when we clearly understand the system behavior and can define the explicit rules for the action. The second approach is about the model-based analytics, and this relies on mathematical or statistical models to describe the relationship between inputs and outputs in the system. Um, and these models can be, for example, the data-driven model, or it can be the physics-based model. In data-driven model, where they learn from the historic data using machine learning, and while the physics-based models are models based on the fundamental laws or and the engineering equations. So model-based analytics is particularly powerful because it is adaptive, and meaning it can learn from the data and generalize to the new unseen situations. That makes it well suited for complex nonlinear systems, where the traditional rule-based methods might fall short. So depending on the application, we can choose between these approaches or even combine them, make a hybrid model for a robust industrial analytics. Okay, so Uh, now let's look closely on the physics-based technique, which are a key part of the model-based analytics. These techniques assume that you have already a good understanding of the knowledge of the system and requirements and equipment that we are analyzing. And in other words, we know the physics that is governing and how it should behave. The physics-based models use this domain knowledge and combine them with the measured data to estimate the performance or the predict the future of the equipment, like for example, degradation or the remaining life or the failure trends. Okay, for example, failure trends. Okay, or anything like degradation. Okay, so when we compare physics-based methods to data-driven ones, we find several clear advantages. And what are these advantages? The first one is about that they typically they require less data because the models are built on the known physical laws, so they require small data sets. Secondly, they are capable of making like long-term predictions, which is very useful in applications like predictive maintenance. This is good in predictive maintenance. So so you may come up with a database predictive maintenance model, but if you are not incorporating the physics-based methods, your system will fail after some time. And finally, uh, and finally, we have this uh, the physics-based models. that are normally they are more reliable. Yeah. And especially in especially 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 in safety critical application systems. Okay. So, however, these models also have a limitation. They require very deep technical knowledge for the system. So they are good, but they require deep technical knowledge. So yeah, we need to fully understand how the machine works, any factory or machine works, in order to model it accurately. And that's not always easy or scalable in every industrial setting. So while physics-based analytics are powerful, so let me write, while physics-based analytics is powerful, they come with the sort with trade off of complexity and expertise requirements. Okay, this is the challenge. Okay, now let's talk about the second category of the model base, which is data driven. So they rely on historical data. They rely on historical data, and uh, they under the normal condition as well as the failure scenarios. Okay, so not historic data that has both a normal and the failure history. So the techniques such as machine learning and statistics, machine learning and statistics, and even the deep learning, um, they are used here to recognize pattern. And basically what we are trying to do is we are trying to find some patterns. Okay, so find patterns, recognize patterns, and make the prediction. But the key requirement is the what is the key requirement? We need lot of data. Okay, for this we need lots of data, all sort of data to train it, and it must be relevant, clean, representative for the actual system behavior. However, in many real world scenarios, even if we have a detailed mathematical model, it may be too complex or time consuming to solve them. So this is where the surrogate modeling becomes very useful. So in surrogate modeling, basically what we do is, in surrogate modeling, what we do is it is a simplified approximation. Uh, it's a simplified approximation of a process, and it's fast to compute and easier to analyze. These models are often trained using the data and simulation results and are used in place of the full physics-based model. So when we cannot apply the physics-based methods directly to due to their complexity or computational cost, the surrogate modeling allows us to still capture the essential system behavior using less computational power while maintaining the reasonable accuracy. So this flexibility is one of the reasons surrogate models are becoming increasingly popular in industrial analytical workflows. Okay, right. So this is in this slide, when building the analytics, one important question is how much data do we have? And so how much data we have to we have how reliable it is it. Okay. So theoretically, if the number of data entries equals the number of unknown parameters, model parameters, we can identify the system. But in reality, things are rarely that simple. So due to the noise, practically, practically we what we see is we see the noise and missing context, lack of contact, and lack of context or uncertainty in the data. We often need many more samples than expected. So that's why the data driven methods require large data sets, large amount of data. So we require in data driven model, we need large data sets, especially when the machine learning using the machine learning. On the other hand, the physics based methods, they require less amount of needs few samples, because the model already includes the physical laws or governing equation, and they need to find out their own few parameters. So to help decide which method to use, we can look at the very simple decision table here, this one. Now, so if we have a small amount of data and low reliability, then the basic rule-based approach may be the only option, but they would not be very accurate. Okay, very simple rule. If the data is small but reliable, we can then use the physics-based analytics is preferred method. If you have a large amount of data, but it is noisy or inconsistent, you can still go for the data-driven approaches like the machine learning. And ideally, if the data is both large as well as highly reliable, then both of these things can be used. Okay, so it means that the data is large as well as and reliable. If that this if data is both large and reliable, it is choice that you can use both physics based model or data driven technique. So this decision framework is important to keep in mind when planning the analytics of industrial systems, and we know how what is the result of our system. Okay, I will stop this recording here, and the next topic will be in the next recording. Thank you very much.